There's a growing question that is almost hard to believe. More and more people, as time goes on in this, modern, technologically advanced world where we have satellites and spaceships and planes flying around the world, how is it that despite our ability to experimentally prove or disprove things, we have a growing consensus of people who are absolutely sure that the world is flat? Well, today, through popular request, I'm going to be speaking to David Weiss, who is a renowned flat earther online. And my ambition today in this conversation is to try and understand the formational building blocks of how someone gets to the point of believing, understanding, and in fact, according to themselves, proving that the Earth is flat. So as we go into this conversation, I'm going to try my best to avoid the typical debates and try and see eye to eye as much as we can, because while this is an episode I wasn't 100% sure about doing on the channel, I have to say that it's been a real journey for me to try and get inside the heart and mind of someone who believes the Earth is flat, and who knows, maybe on another episode I might just be able to change his mind just a little bit. Hope you enjoy this one. Here we go. I gotta ask, David, would you mind introducing yourself to my listeners and sort of let them know a little bit of the fundamentals of what we're here to discuss today?
Yeah, so I'll keep it short. I was just a normal guy, grew up in America, was in corporate America, had my own business, and I was doing a little podcast on the side about a lot of the deceptions in the world. We called it Deep Inside the Rabbit Hole. It was kind of a big podcast, and in the third year, people like, hey, Dave, have you ever looked into the idea that the Earth might be flat? Right? Now, we were open-minded to anything, like, 9/11, all the stuff. Go ahead, bring it. Let's investigate. Flat Earth, not looking. You're an idiot. Ban for life, ban for life, ban for life. I would just ban people for even suggesting that I look at it. But then I was forced to look, and I went in with a closed mind. I went in to debunk it. I just said, I'm just going to put this Flat Earth nonsense to bed. And for 2 weeks, I didn't sleep at all. I'm looking and trying to debunk it. And the harder I looked, then I realized I never looked. There's people in the world. I know the Earth is not a globe. I know it's a level, non-rotating topographical plane. And anyone that thinks it's a globe, they don't know why they think it's a globe. They've been programmed and they have no proof. They go, oh, there's tons of proofs. Let's hear one. And every one that you have, I will completely dismantle, proving that it's not real, showing you the absurdity, the mental gymnastics that you need to do to live in a heliocentric world in a space vacuum, which is just scientifically impossible. And then the smart person will throw their hands up and go, what difference does the shape of the world make? I still have to go to work on Monday. I know that's what you were thinking because we were all programmed to say it, right? But the truth is, this is the fundamental lie, the foundation of the world that you live on, your understanding of this place. And this is the one that keeps you a slave for the corporate slave masters of this world. They're literally farming us with their corporations. And once you see it, you can't unsee it. Nobody leaves Flat Earth. I was showing you a moment ago on my app, the heat map of the people that just have my app, which is less than 1%. And we just hit 200,000 people. There's millions and millions and millions of people. Last thing, and then I'll throw it back to you. I think it was like 4 or 5 years ago in Brazil, they took a survey in just little Brazil, and 11 million people said they didn't think the Earth was a globe. That's just in Brazil. That was 5 years ago. And now, 5 years ago, 6, 7 years ago, you'd say, hey, you want to talk about flat Earth? They're like, no, you're an idiot. Now you're like, this is interesting. Let's have a conversation, because you can't put the genie back in the bottle. So there you go. That's about me.
It's a lovely way to introduce the conversation because, like you say, it's a growing trend of people subscribing to this idea. And that's actually what I'm really trying to understand. And as I try and understand that, could you take me to one of the first or one of the most powerful pieces of evidence and observations that you remember being the reason why you went, aha, eureka moment, I can now see factually that the Earth is flat?
Yeah, people always say, what's the best proof? What's the best proof? And it's different for everybody. It really is. It's different for everybody. But what got me, because I live in the same town my whole life. I'm a guy, I'm a a kite surfer, windsurfer. I've been on the water a lot, and it's the boats over the horizon. We were all shown that three-masted ship going over the horizon in elementary school. And when you go back and look at that, you can see the deceptiveness in it. Yes, things do disappear from the bottom up on a stormy day on the water, but that's not because of Earth curvature. It's not because of Earth curvature. Before we go any farther, I just want to say, for those of you ready to turn off this button saying that Mark has lost his mind, I offer 3 Bitcoins for 1 globe proof when I'm done. 3 Bitcoins, 1 globe proof. That simple. All right. So it was boats over the horizon. So here is, you have to understand about perspective. We look out here. This is supposedly the horizon of the ball Earth. And do you see a boat out here? No, you don't. But as we zoom in, we're making the angular size bigger. So as we zoom in, we're increasing the angular size. And as we do, all of a sudden you'll say, oh, look, there's a boat. Where'd it come from? Was it over the curve? Now watch, I'm going to zoom in on this boat. These little waves in front of the boat, like my finger, can't hide the boat until the boat gets smaller. And then it can. And the boat looks like it's disappearing over the curve of the Earth. But it's just the way that we see. The boat is getting too small for the little tiny waves in front of it. And the little tiny waves in front of it are creating a false horizon.
Well, for those of you who might be listening and not seeing Dave's video, of course, you can watch this on YouTube and see it for yourself. We're looking at a video where you're zooming in over the horizon. The kind of angular size of the shot is opening up, and you can see a boat on the water on the horizon. And thank you for that. And the 3 Bitcoin element is interesting to me. So 3 Bitcoins for the proof that the Earth is a globe. I like that. Proof. Now let's rewind very slightly, because what would be really cool for me to try and understand is, could you try and make a summary of how you believe the model is working? So instead of necessarily looking at these images and videos for the moment, because we'll get into these later, what is your structural belief that the Earth is, as far as I understand, just talking to you in this conversation, we've started with it's flat, similar to like a plate. We can imagine just a flat circular plane, correct?
Well, yes and no. Not, we say a plate that's like a disc floating in space. If you search flat Earth images, you're gonna come up with what they're gonna feed you, a disc floating in space, something like this. This is the first image that Google will serve you, which is a pancake Earth floating in heliocentric space and water falling off the edge. That's not flat Earth. The only people that think that's flat Earth are people that believe in the globe. And they're believing in 2 false things. They say, oh, what, are all the other planets flat? Are we the only pancake planet out there? This is a fake heliocentric system with a fake flat Earth floating in it.
And heliocentric meaning that flat Earth would be orbiting the sun, i.e. the sun is the center of gravity of our system.
Yeah. So we live in a heliocentric, globular, gravitationally held together, which is insane if we get into gravity. Everything in our sky works like a clock perfectly. It never changes. It is the definition of time. A Swiss watch, the finest Swiss watch in the world, is less accurate than the sky clock. But we have gravity holding on to things. Like when our moon comes around the Earth towards the sun, how come it doesn't speed up? And when it goes away, how come it doesn't slow down? How come the sun's gravity, the sun, is helium and hydrogen, which defy gravity here on Earth, but for some reason in space, instead of violently filling the available space, they collapse upon each other. They make a sun, and the gravitation of that is able to hold on to Pluto, which is an unfathomable distance, but it can't hold on to our moon. It can't affect anything else.
One of the things I want to do first, and forgive me for trying to rewind to those basic principles, because obviously when we talk about pressure, gravity, we can explain those things about how the sun works. I mean, the sun's gravity does affect the moon and Earth, all planets in our solar system, for example, or the moons that orbit them. And I'm interested to get into that. I've made a little note here. But in terms of the basic principles of your belief, so we have the flat Earth. You don't believe it's like a spinning plate that is just in the vacuum of space orbiting the sun. So let's start by building up. We have the flat Earth. We're trying to imagine looking down on like a 2D map, if you will. Where are the sun and the moon in your model? How do they function?
So the sun and the moon are small and local. They're the same size, just like they appear. If this is my app right here, we're looking straight down on the Earth. The sun is the hour hand, and wherever the sun is.
And again, please forgive me for jumping in, Dave. I didn't mean to interrupt, but just for the people for the people listening and not watching, we are looking essentially like a clock. We have a 2D circle with like an ice wall around the outside of it, and we have a light source, the sun, which is illuminating kind of a perfect half of this circle as it's moving around. So please go ahead, Dave.
It's illuminating the perfect half right now because we are right at the equinox. But if we move forward throughout the year to like December, the shape of the light changes because it gets closer to the dome and the light wraps around. That's a little higher education that we probably won't.
I was going to say, if you don't mind, this is useful to understand as we get a fundamental concept of your model. Who's changing the light? Who's changing the distance that the light rays are moving there? I can see that the light, instead of now illuminating half of the Earth, the light is now bending around the sides and it's illuminating more of the Earth. So who's controlling that?
Well, who? I mean, this is a created system, an intelligently designed system. So we can decide who all day long, but I'll just say the creator. The sun migrates in between the two tropics. On June 21st, since we're in December, on December 21st, it's making its outer largest, fastest loop. Not fastest, longest loop. It takes the same amount of time. And it goes over Australia. So in December, it's summer in Australia because the sun is over Australia.
Okay.
But it's cold in the north because the sun is farther away. When a street light is above you, it's high above you. We'll say that's your summer sun. But the one down the road is farther away and it's lower in the sky. That's your winter sun. So for us in December, the sun is far away. It's cold. It's lower. But 6 months later, the sun will move into the Tropic of Cancer. And that's our summer sun because it's higher in the sky and it's cold and it's colder in the south.
So I have one question on this.
Yeah.
We have the map with two kind of concentric circles, one on the outside, one on the inside, and they're the different tropics. Yeah. And the sun moves on these different paths. Does the sun travel faster on the longer path?
Yeah, it has to. How would it get around if it didn't?
Okay, so here's maybe the first challenge. I'm not expecting you to transfer me any Bitcoins just yet, but if on your model that we're looking at, the sun we know has to travel faster on that outside journey in order to make it in the same time that it travels on the inside journey. Clearly the inside journey is shorter, the outside journey is longer. If it's going to do the outside journey in the same time, it naturally has to move faster. We would be able to easily make an assertion between me and you as collaborative people trying to find the truth. So me and you, we're on the same page and we're trying to understand if this model is accurate. The sun, assuming I understand your model correctly, in the winter would move across the sky slower than it would move in the summer. In the summer, this sun, as you've just described...
Wait, what are you talking about, our summer or their summer?
Well, we can both agree that... summer in England is winter in Australia and vice versa.
Okay,
we're both happy with that.
So I just want to know which one you're talking about because I think you said it backwards. You said it's moving slower in the winter, but it's in the winter, in December, our winter, the sun is moving faster.
Yeah, actually, you bring up a really good point. So just to clarify exactly what I mean, in the arc, which is longer, where it has to move faster, you're absolutely right to correct me. And again, I guess we're collaborating here, aren't we? Because we're trying to find out the truth. Would it not be very easy to observe the sun moving at different speeds, right? You'd see it moving faster in the summer than you would in the winter.
Yes and no, because the first thing is we see what's called, it was called as our personal azimuthal dome of vision. We see in a dome, whatever distance we can see in all directions, infinite number of points creates a dome of vision. This is not a flat earth thing. This is how the globe describes, marks the sky. But we see in this dome of vision. So the angular rotation of the sun will look the same. The way you can tell that it's going faster. So in the summer, in the UK, here in Connecticut also, when the sun sets, right after set, it's still light for 90 minutes to 2 hours. The light is still there for like 2 hours, right? But in the winter, when the sun sets, it's dark in 15, 20 minutes.
Because it's lower in the sky.
Because it's lower in the sky. But here's the thing. If the Earth was a ball, we're tilted, and 6 months later we're on the other side, so the opposite, there would be symmetry in the south. the South would have longer sunset to darkness than in their summer. But the truth is, if you measure from June, everywhere in the world, and it's different for everyone, topography matters, everything. Your personal spot from sunset to darkness gets shorter for everyone in the world from June to December. And then from the end of December back to June, it gets longer because the sun is slowing down. So there are places. Last point.
Okay.
In around this time of year, November, December, there's places in the South when it sets 5 minutes later, it's pitch black. 5 minutes, and that's because the sun is whizzing away much faster.
So, as we're trying to explore this problem together, one of the assertions that we are sure of is that the sun's velocity changes.
It sure appears to.
I mean, I feel like that might be our first question to really try and drill down on and try and get an answer to that we can both agree on, because we can both measure the angular velocity of the sun, and we can. I know what you're saying about individual domes, but let's assume that we have
the angular velocity
friends.
is the same. The angular is 15 degrees per hour approximately.
But did you not contradict yourself there? The angular velocity would change if the speed of the sun was
no, it wouldn't. Watch.
Augmenting.
Here's the hour hand, and if the sun is here over Cancer or out here over Capricorn, it's going 15 degrees an hour. It's going around at the same angular speed. Its tangential speed, its velocity is changed, but the angular speed is exactly the same.
But then you could also counter this by the relative angular velocity of the moon as well, because what you're saying is that the angular velocity of the sun is the same, but the speed of the sun changes. If I've understood,
yeah,
you
the
correctly.
speed of the no. So here's the thing: you see it move through your dome of vision at the same rate all year long, right? It doesn't matter. So if you get a glass dome, put a glass dome on a table, and then take a light and start from one point and go 180 degrees around at whatever speed. So when I say whatever speed, 180 degrees, and let's say you take 1 minute to do it. Then make a bigger circle, but take 1 minute to make that bigger circle. You'll still see the sun in that dome make the same path in the same amount of time, even though it's going faster.
Okay, I see. So then there is now a mechanism which is moving the sun from being on one tropic to the other tropic and vice versa.
Yeah, so this is the thing. When you say a mechanism...
I'm trying to understand if this is correct, then as you say, according to your model, the sun exchanges its orbit from this inside path to the outside path. How does that work? How is that moved radially further or closer?
Well, here's the thing. Looking up at the sky...
And also, forgive me, my last thing is then, wouldn't the seasons not...
Okay.
When the seasons happen at different rates, because summer and winter, they're the same length, right? So,
Mark,
I'm with you. I'm trying to be with you.
You're scalloping a little bit. Let's. I can't wait to talk about seasons, but you asked me another question first.
Yep.
Then I'm going to show you that how the sun doesn't follow 15 degrees per hour, and then we're going to go to seasons, and then we.
I thought you said it does, though. I thought you said the angular velocity of the sun is always 15 degrees.
It is just during the day, but it doesn't go below the Earth and continue to do that. I'm going to show you that in a moment, right?
Okay.
So here's a little experiment you can do. You get a flashlight and flash it on the floor 3 feet in front of you, okay? So from your feet to it is 3 feet, about, whatever. And then spin around, take 1 minute to make a full rotation, okay? And now you drew a circle 6 feet in diameter, 3 foot radius, right? And then point the light 6 feet away from you. The light has barely moved. It just changed its angle just a tiny little bit. And then spin around at the same rate. You just drew a 12-foot radius circle in the same amount of time without this ever moving. Its focal point just moved just a little bit. Just a little bit. I'm not saying that's how it works. I'm saying there's an example of how it could work. Looking up at the sky to figure out the shape of the Earth is like a guy coming in to put rugs in your house and measuring the lights in your ceiling to figure out how he should cut the rug. It makes no sense.
But okay, but on that point, and again, I'm looking at this conversation in a way that we can collaboratively strike out certain things through observations we can both make.
Yes.
Because while I'm still a little bit confused about how the length of the season stays the same with a sun that changes velocity but maintains its angular momentum, I think you're going to help me with that in a minute. But that's the first challenge. And the other challenge, you say, if you're on a globe looking at the sky, that doesn't help you make an assertion of the shape of it. And where I would disagree with you is if me and you took a trip to London, which is, obviously where I am now, and we could look at the sky and we could, take pictures or video over a long period of time, you would actually see, the rotation of the stars around Polaris. And if we went, to Australia together, I'm not saying you believe anyone, we do this together collaboratively, we would actually see kind of almost the inverse of that. And then on the equator, we'd see that the stars almost go horizontally across the sky as if as if there isn't any twisting around at a particular point. So between me and you, we can actually both agree that by looking at the night sky, we could really make a clear assertion of the rotation of this body that we're on.
I disagree.
And okay, and why? Why do you disagree with that?
Well, we're gitch galloping. We're leaving all of these other things behind. Let's try to go in order. You want to write that down? We'll hit that after seasons. But I want to cover the other two things that you brought up without just dismissing them. Is that okay?
Yeah. Okay. Yeah. Fine. I'll be keen to come back to that, but I'll follow your.
Yeah. So we have the sun. And the Earth is rotating, so the sun appears to go around the Earth like that, right? Of course, the sizes are wrong here. This is a distant sun. It looks small, right? So the sun goes around. So because the Earth is spinning at a certain rate, the sun has to move consistently at that rate. Okay? We can agree with that. You agree with that?
The sun's not moving.
The sun is moving, but relative to us, it's the Earth's spin that makes the sun rise and set. Right?
Yeah, I guess for clarity, I always have a little voice in my head saying for people listening who didn't see, you were holding an orange smaller ball and a globe, and we were kind of moving them. But as you rightly say, from the perspective of the Earth, if we're looking at that model as the kind of our viewpoint, it's not like the sun is moving around the Earth. The sun is relatively stationary as the Earth rotates.
Well, if you knew the actual motions of the sun, you wouldn't say that. But for the sake of this conversation, we can just say that the reason the sun rises and sets is because of the spin of the Earth, and it's moving at 15 degrees per hour. Now, we watch the sun, it goes down, 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 and it should just keep on going. It should never stop, right?
Why?
Well, because the Earth is spinning, and if it stopped, that means the Earth stopped spinning. The sun, when it's setting, it should never slow down. It should just keep on going and then come back around the other side of the Earth and come around again, right?
Well, it depends where you're from, because, for example, if I go to the northern tip of Norway, I might not see the sunset at all because
okay,
of the
that's
tilt
fine. But the sun won't stop moving. It'll move in a circle at 15 degrees per hour. That's required for it to go all the way around the Earth in 24 hours. 15 degrees per hour times 24 hours is 360 degrees.
We are on the same page. I mean, obviously, the path of the sun, depending on where you're standing on the Earth, wouldn't always look like a circle.
I'm not talking about that. I'm talking about if the sun was setting and then it stopped setting. That's a problem.
If the sun was setting and you were in a location in the northern hemisphere in the summer, you would see a position where the sun would set, look like it temporarily stops and then rise again.
No, I'm talking about here in Connecticut where we never have 24-hour sun, where we always have a minimum of 8 hours or more of night. So I'm
convinced that in Connecticut you wouldn't see the sun stop in the sky.
Very good, very good. So we can agree with that.
Okay.
So I was filming the sun on a super clear, cold day with very low humidity, and that's what matters. It's the atmospheric deck of opacity that hides the sun.
Sorry?
I call it the atmospheric deck of opacity. When you're looking up at the sun, up at the stars, you're looking through a very thin layer of atmosphere. When you're looking 45 degrees away, you're looking through, I don't know, maybe 3 or 4 times as much atmosphere. But when you look across to the horizon, you're looking at 100% atmosphere. And over distance, that becomes opaque. And that becomes your optical horizon, or what I call your horizontal eye zone. So we're not talking about that right now. We're talking about the sun. I'm watching the sun go down, 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 down. And then when it got to this horizon right here, it stopped. and it sat here. Now I have this sped up like 1,500% or whatever, and it just sat here. Now my friends were at the beach over here, and they saw the sunset from the bottom up 10 minutes ago, but I'm still watching it, and it stopped going down, and it just sat here. It's sitting here, and it starts getting weaker and weaker, and then all of a sudden it fades into the thickness of the atmosphere. It just literally fades out. It just fades out. And it didn't go down. Here's the thing. I don't care if it's out of focus. The Globers will say, where's your solar filter? Put a solar filter on and you can't see this. Take the solar filter off. The sun went down, 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 and it stopped right there. I'm going just forward and backwards here. And it stopped going down, which shows you that it's just going away.
Okay. Let's say that me and you can agree on the video looking as if the sun has stopped. So we can collaborate with that, and we can say we're looking at a piece of what seems like evidence that the sun has been setting and then it seems to have stopped.
It actually did stop.
Okay. From what we are looking at, it seems that way. And again, as collaborative scientists, we got to try and understand, has what we've seen equated to physical fact? And I think that we are going to have to go back to some of our earlier principles to get into this, because I believe that there could be lots of other elements at play to this video looking like this. Whether you look at lenses of cameras, whether you look at atmospheric lensing, whether you look at refraction, whether you look at the angles, whether you look at the weather patterns if you had high density air in a location in front, low density air.
What would stop it from going down? What would stop its downward momentum?
Well, I don't believe that the momentum of the sun has stopped. I believe that the image gives the appearance that the sun has stopped. But that's not actually what's factually happening. And this is really why the evidence is important, because these videos that you're showing, it really helps me to understand the psychology, the experimentation you've done. And I have to give credit where credit's due, that I can understand when I see these things how it's hard to discern sometimes, right? Sometimes you can look at the video and it really does look, for people who are listening, it really does appear in that video as if the sun has kind of stopped and then started to fade away. And now the job between me and you is to try and, for the sake of the truth, I want to be friends here. We want to collaborate as best we can. And my fear is I want to make sure that you're being upheld to the most scrutinous ways of looking at this data, and you for me. And between the two of us, we're really going to get somewhere. So, in your model, what is it that made the sun stop?
It's just because the sun circles around when it comes into our view beyond the horizon. And now we can get into what the horizon is. The horizon is well above your eye level, and the sun is just beyond it. And I can show you that. I just really want to drill down on this evidence you have of the sun stopping. I want to make sure that your model makes sense, that you've just seen the sun stop on the horizon. How does that work with your model? Because the sun is going away. So you see it going. The sun makes us from when it comes into view, it goes up on a sharp line to the point directly above you. Then it goes down. And when it gets near the horizon, it usually goes beyond the horizon. And it disappears from the bottom up. And I will show you that in a moment when we get to that. But it goes beyond the horizon. You made a comment a minute ago that the moon is a sphere. Here are 4 spheres. Actually, they're not 4 spheres. Is this one a sphere? And if I look at it and I pick it up, well, it's a half sphere. So that's kind of weird. Is this one a sphere? Before we pick it up, what do you think? It looks like a sphere, but actually it's flat, right? Unless you can touch it and measure it, you don't know what shape it is. Is this one a sphere? It looks like a sphere, but it's not flat. It's not a half dome. It's actually a cup. It's a bowl. So I don't know what the moon is. I don't know.
Okay, so let's focus on this moon thing in 2 seconds. That was just a very slight step back. I do just want to understand in your model of how this system works with the sun and the moon moving in these kind of concentric circles. In your model, what explains the sun stopping? You said it's just moving away forever on the horizon.
I will. I can show you now.
And I guess this is also important to me because you did say earlier that the angular momentum of the sun across the sky is always 15 degrees per hour. So what I'm worried about is,
we see it move approximately 15 degrees per hour, except when it's very low on the horizon. Then it gets blocked by the horizon, not by going below a ball horizon. It goes beyond a horizon, and I will explain that fully right now if you allow me.
Please go ahead.
Okay.
And then we'll come back to these balls.
Sure. So we're in New York City. We're looking straight up. There's a 50-story building, and it's 12 noon, and the sun is directly above me. So let me ask you a question. This is a very easy question. It's not a trick question. The sun is moving. Let's say it's 12:30 now and 1 o'clock, and now the sun is out of view. Is the sun below the horizon, or is it beyond the building?
If we are defining horizon as ground level, then clearly it's not below the horizon. It's been obscured by the building, correct?
Yeah, okay, very good. So here is, we were taught part of perspective that the sky ramps down, the ground ramps up, the sides ramp in, you have your point of your perspective. So I got a guy here, he's looking down, and this line right here is his horizon.
This, by the way, for people listening, if you imagine that you were in a like a white room with grid lines going across the ground into infinity, and it's like a tunnel, a square tunnel, and you had grid lines going on the walls and on the ceiling. So you imagine this almost like grid lines going down into infinity. That's what we're looking at here. So please go ahead.
It's called the perspective grid of vision. So I throw a mountain in front of this guy, and let's say this mountaintop is 3,000 feet above his head. Okay, no problem, right? These are just, nothing's to scale here, but he's standing next to a mountain. The mountain's 3,000 feet over his head. The sun's high in the sky, and the sun moves again. Is it below the Earth horizon, or is it beyond the mountain like it was beyond the building? Easy question.
If you're to define the horizon as sea level, then it's not. At least we can't tell if it's below the horizon. It's just behind a mountain range.
It just went beyond the mountain. Very, very, very good. And I say the horizon. When I say horizon, I'm talking about the globe horizon, which is the physical curve of the Earth, the edge of the Earth, because that's what you guys call the horizon. In flat Earth, there is no physical horizon. There's an optical horizon. We can get into that, but so. The sun's beyond it. So this guy can go up or he can go backwards. Let's move him backwards. We move him backwards 25 miles. And now the top of that mountain looks like it's at his eye level, but it's still 3,000 feet above his eye level. Like, I can look at New York City. I'm 25 miles away from New York City, and the tops of those buildings look like they're almost at my eye level from that distance. That's just perspective. That's how it works. Look over water at any land, you'll see that the trees that are a couple hundred feet above your eyes look like they're at your eye level. So we got the sun in the sky, the sun goes away, and it goes beyond the mountain, like it went beyond the building, like it went beyond the mountain earlier. Put the clouds in here, so now we have the atmospheric deck, right? So the sun is above the clouds, and the sun moves away. Now, what is this line here that it's going beyond? This line here is the top of the mountains, 3,000 feet above his eyes. It's also the cloud deck, the atmospheric deck, which is 10,000 feet above the mountain. So this line here, this opaque line that is thousands and thousands of feet above his eye level, to him, it looks like it's at his eye level. And the sun just goes beyond it and takes its light with it.
Okay, now I just want to try and double down on what the observation is here. So what argument are you making in principle?
What I'm making is the sun doesn't go below the horizon. The horizon is not at your eye level. The horizon is thousands of feet above your eye level, and the sun just goes beyond it. And optically, because of perspective, it looks like it's at your eye level. It looks like it's at your eye level.
So then let's take a slightly alternative example where instead of there being a mountain range, we're just looking over the sea, where we know that there isn't any perspective gains there. It's just a flat surface relatively from where we are. So we're looking to what appears to be this completely flat body of water. There's no mountain ranges to hide behind. The sun in your model is just moving so far away from us that because of the loss of light from the source through the atmosphere, it seems to just slowly fade away into darkness.
Well, usually over water, you have the marine layer. That layer becomes opaque. It's hundreds, if not thousands of feet above your eye level.
What's the marine layer?
It's just the marine layer. It's the thickest atmosphere is usually over the water. And just look up marine layer. It's literally, it's just thick atmosphere, and over distance, it becomes opaque. If you're in an Olympic-sized swimming pool, the water looks perfectly clear. Go to one end of the pool, you can't see the other end of the pool, even though the water's clear. It's called the thickness of the atmosphere. The air is just like water.
But I mean, this again is something that I think we can both easily check. We can look at the density in bar of what's happening in weather systems. We study this quite closely. So we would be able to actually know factually what the pressure of the atmosphere over water is and over land is, and we would be able to not only measure that, but observe that that isn't the cause of loss of light. You can put light through different pressures of atmosphere, and you wouldn't see light lost at that amount per distance. We could do that together. That's not something you need to trust me on. We could test that together.
So here I have a shot. We got our line. It looks like our horizon.
Okay,
now,
fine.
These clouds up here are the same height as these clouds, which are the same height as these clouds. And you not only do you have perspective going from the sides and the top and bottom, but it's from the back forward. So
agreed, fine.
So like from here to here, that could be 100 yards. From here to here could be 25 miles. So it's all being compressed. Now, is this sun setting? It's the end of the day. Is the sun setting?
If I were to draw a pencil around the circumference of what looks like a larger sphere, I would say it looks like just the bottom part of the sun at this point has began to set, because it's I'm
glad you say that. So now let's zoom in and see what our eyes can't see. So if I zoom in on this, there's actually a lot of space here. It's still way high up in the sky, but the way you see it makes you think that it's setting. Right? It's up here in the sky. It's not setting. It's going away. It's going away, and it's going to go beyond, just like it goes. There's an atmospheric deck of opacity here. You can't see it. The sun will disappear from the bottom up as it goes beyond it, just like it did with the building in the mountains.
I think that what you're explaining here could be paralleled with looking down a train track. If you're in the middle of a train track and you sort of see the two lines, and they're straight lines, are parallel, but they look like they kind of converge, similar to the reflection in the water that we see in this video. And the example that I want to give is, if it were nighttime and someone shined a laser pointer in your eyes, you would see, quote unquote, this kind of wider warmth of light. It would be kind of dissipated to some extent because this very bright light is hitting your eye. Now, of course, if you had a camera and you could change the aperture and you could reduce the amount of light it was reacting to, you would see that that's actually a very, very tiny point source. It just feels like it's a wider, more diffused source of light because that's how light works, right? It comes through the atmosphere, scatters around. So you kind of, it's a nice demonstration, and I have respect for the demonstration because it is, again, an illusion, right? You look at the sun, you think it's setting because you kind of draw that penciled circumference, just like I said, naturally, and it looks like the sun was actually below the horizon. But actually, based on the aperture settings of the camera, the amount of light that was coming in, we're actually looking at a more kind of like the halo of the sun, a bigger, let's say dispersion of light. And yes, as you change that camera setting, as you zoom in, you can clearly see that it actually hadn't really started setting. If you can
okay, well
say it like that.
Now let me show you the other part of that with what I call the opaque part of the atmosphere. So here we have streetlights. We know that they're all the same height, but they literally merge into the horizon. Here is the sun. Going through the sky, and it's literally going down at the same perspective angle. This is a local light, and it goes into here. So now, what is in between that last sun and the ground? Can we actually see it? So let's look at this.
Well, may I briefly go back to the previous one?
I'd like to make a point, though.
Fine, go ahead.
I'd like to make a point. So this is a little hard to see. You see this line right here? I have a string that goes here.
Yep.
Now, this string is level. It's not sloping down. But this is a terrestrial point of view. This string here is the same string filmed from a celestial point of view, from the height of the string. This string here is the same as this string here. Now, I'm going to slide this light along the string, and as I do, it's going to go behind what I call the atmospheric deck of opacity. Here is the real sun. Now look, remember that sun I just showed you that you said, oh, that's because you can't see it, whatever. You can't see with your naked eyes the line from where this is setting to where you think the water is. That all becomes the same line as I zoom out. So this sun looks like it's doing exactly what this is doing. This is level. This is just moving along this line, and this one is going beyond this atmospheric deck of opacity. Now look, watch the sun. It looks like it's setting from the bottom up. You can't see the distance between the water and where the sun is setting when you zoom out. It looks like it's all the same line. Okay. That's how the sun sets, over water with no land or anything in the way.
Could you rewind to the previous slide that you had with the street lights?
Sure.
Because one thing that's quite important to me is, again, we focus on the basic principles, and we'll come back to those. The videos and the evidence that you're showing, like I say, it's compelling in the sense that it looks like you can make certain deductions from it, right? It looks in a certain way, and I believe that there's reasons for that. But again, me and you were working together on this podcast. We are trying to find the truth between the two of us. And what I'd like to try and do here is maybe a little bit on the fly, try and challenge something that you've shown me. This kind of goes back to the angular momentum of the sun and the seasons, because I have to keep making sure we can see eye to eye on this. The picture, for the people listening, we have a comparison on the top of streetlights, which are evenly spaced streetlights, and they go off into the distance, and you can see this almost like straight line convergence, almost to a point source. And below, there is a time-lapsed photograph superimposed of the sun moving through the sky. And because the time between the pictures is the same, they're kind of the same paralleled, right? The streetlights are equidistant, the time between the pictures of the sun are equal. Now, the thing I want to try and understand, according to your model, Dave, because this is your evidence and this is your model we're trying to understand. One thing that strikes me in the picture below is that there is an equal distance between the different pictures, right? So the pictures are snapped at the same time, couple of seconds, or 15 minutes, whatever. And the distance is the same between each one of those suns until it goes.
I don't know what the interval was. Maybe they slowed down. Maybe
I'm gonna make an assumption.
Maybe there was 100 other pictures they took out and they just picked them so it was evenly spaced. We don't know. You can't assume.
Well, okay, you're right. You can't assume, and I'm glad you said that. You can't assume this, and what I want to just keep bringing this conversation to is I want to work on principles that both me and you, irrespective of one another, we can actually just go and repeat this and check this ourselves. Because if you did go to the same place or many places, and you took pictures at frequent, consistent intervals, you would see the picture that you see on the bottom. And what I would like to just question is, why is it that in the comparable pictures, the light sources on the top have a big distance, and then the distance gets smaller, and the distance gets smaller, and the distance gets smaller from our perspective until it almost merges into a bright white line, when the picture below, in the same way, isn't
because the picture below was taken. Let's say there's 20 suns there. Maybe they took 400 pictures and they just spaced them out to show the line that it makes. The street lights, you cannot change the street lights. You cannot change the position. So they certainly merge together. But why would you do that? If you're trying to do a sunset, you're just going to keep them spaced out so you can see the line. You wouldn't let them merge together because it would ruin your picture.
But here's the important thing to contend with.
You should do that. You should actually go take pictures and see if it changes.
Yeah, I'm with you. But the bone of contention for me is the picture below. You're expressing the sun as moving off into the horizon. Now, through your own perspective argument, if the sun was moving consistently away from you in the horizon, you would actually see, from your perspective, you wouldn't see a consistent distance between the suns on a consistent interval. They would appear to group more and more together as it got further away.
100%.
So, okay, but hold on. Let's just put a super pause on here. If you agree with me 100%, can you explain how your model allows this to happen? Because yes, I think you've contradicted yourself.
I explained it already. You're not listening. So
okay, my apologies. I'll try better.
Let's say they took a picture every 30 seconds, and the first couple, they said, okay, you know what? We're gonna every fifth picture we're gonna do, and then they realized later that the fifth picture was still overlapping, so they took the seventh picture. And then they realized, they got to wait a little longer. They're not gonna pick them so they're overlapping. You're going to pick them so it's evenly spaced. They picked it to show you the path.
Nobody. And then my position would be: you don't have to pick it. You can do it yourself. We can both do it ourselves.
You can do it yourself, and I know for a fact that they will overlap. So you have to pick the ones without it overlapping. They're just showing you where it's going. If they were starting to overlap, then their demonstration wouldn't look as good.
May I ask a serious question? If I could do a consistent interval photography experiment to mimic exactly what you showed me there, and we don't see an overlapping, and we see a consistent angular momentum of the sun going through the sky, does that qualify to you as giving me 3 Bitcoins as proof that your model was incorrect?
Absolutely not. As I said before, the motion of the lights in the sky have nothing to do with the shape of the Earth. Like, we're going to get into, I want to hit where you wanted to talk about seasons, and now we're going to talk about the measurements of the shape of the Earth.
Well, also, I want to do that too, and I just don't want to derail you from the moon thing. You were telling me something about the moon, and I didn't want to skip past that. I know you had a...
No, that was it. I was done with the moon. But let me ask you a question. Mm-hmm. Is this cameraman falling over backwards faster than a speeding bullet, faster than the speed of sound, or is this light in the sky just moving away across the flat plane? And it's getting lower because of perspective. It's just moving away. This is a time lapse in Bulgaria on a super dry, super clear day. Now, on the heliocentric model, he's on top of a ball, and that ball is falling over backwards faster than the speed of sound, and the sun just looks like it's going away, but he's falling over backwards. Or is that light just moving away?
Well, it's tough when you say, is he falling backwards at the speed of sound?
Faster.
Because we don't want to conflate velocity with angular velocity.
Yeah,
you know, if you're kind of rotating once every 24 hours,
1,000 miles an hour. That whole thing, you know, the hour hand on a clock is going half the speed of the Earth. No, it's not. We're talking angular speed. If you were on the outside of a merry-go-round, a little kid's merry-go-round, and it was going around once per day, you'd barely be able to tell you're moving. Maybe if you're really conscious, you could say, yeah, I kind of am moving, but this is boring as hell. Then you expand that thing out so it's 24,000 miles in circumference. It's going 1,000 miles an hour, and it's taking a right-hand turn at 60 miles an hour, 60 miles sideways. You would notice that, okay? You would notice that motion. The angular velocity, if you're going on a tangent, any turn off of that angular momentum is acceleration. It's the same force as acceleration. And we are accelerating in 4 different motions at the same time in speeds that are incomprehensible. Okay,
we're going to talk about how forces balance in there, because it depends on your the perspective in which you're going to look at that problem. Because I disagree with a lot of what you've said, but in the name of trying to do things consequentially, out of respect for your arguments, I would like, if you don't mind, to just go back to that moon thing. You started with it. I really didn't get a chance to understand what the point of the 4 circles was. Can we go back to that just so I can, again, have another brick in the wall of what that argument was about? Because I do think that's also important. And then we're going to go back to that kind of understanding of the forces when you're standing on the surface of the Earth.
The point of this was, when you said the sun and the moon are spheres, I'm not saying they're spheres. The moon looks spherical to me. I think it might be. I don't know.
And forgive me, I really don't mean to keep jumping in, but I do want to understand.
You do it a lot.
I know. And I promise you, it's only because I'm trying to understand. So you don't believe that the moon is a sphere?
No, I didn't say that.
Okay, I'm just trying to understand.
I don't know what it is because I can't touch it in measurement. The point of this is, you don't know what shape they are until we reveal it. We don't know how big these could have been the size of yoga balls. These could have been spheres that were gigantic and they're a quarter mile away. But you don't know it until a hand goes in there, touches it, you have some context, and you, wow, that one's flat. You don't know what shape the moon is.
But we do if they're moving.
No, we don't. Because
we do.
the moon...
I can explain that. And what I mean is, here's a good place to really try and double down on, again, my efforts to be collaborative, because I really do want to see eye to eye and make some sense of this between us. This is another optical illusion of some extent. You're looking at these 4 circles, and until they move or they're manipulated in some way, you actually can't tell whether they're flat, whether they're a sphere or whatever.
Right.
So now the best way if I think about how we could explore this together, is for everyone listening right now, they're probably in a room or at least in a car or whatever, just like me and Dave are. You know, if you had, if the moon was flat, hypothetically, I'm not saying it is, but let's say hypothetically, and you imagine you're in a room and you stick a flat circle to the ceiling. Now, you are correct in your assumption, credit where it's due, that if that was stationary, you wouldn't be able to really tell from the distance of looking at it from the floor whether it was a sphere, whether it was flat, whether it was a projection, whatever. But I guess what I'm saying is, if this was to move across the ceiling now, from relative to your perspective, if it was to move far away, closer, further away in a different direction, the perspective of this would almost kind of squash to an ellipse, right? And then it would go back to a circle when it's directly above you into an ellipse. Right. And what I mean to say here is, we both agree that the moon moves across the sky. And now what we have to deduce is it flat? Well, we know it's not, based on our previous thought experiment that we both agree with, because we can imagine and do it ourselves. We don't have to rely on anything anyone else tells us. And then the other part is, if you imagine that, you know, let's say that the moon was a sphere, just for argument's sake, what would happen is, if you went to one side of the room and the other side of the room, again in our experiment where this ball is now just suspended from the top of the ceiling, you went to Australia and I stayed in London, we would actually be able to see slightly different angles of the sphere, and we could FaceTime each other and do the videos and take the pictures, and we would see an angular difference in our perspective of the sphere. So, you know, we would then sort of be able to go, well, that also doesn't happen, right? Because, you know, you're on one side of the room, I'm on the other side of the room, the moon's hanging in the room, and we go, well, we can't replicate that. However, if you then, instead of thinking about this in a room, you shot that ball, you know, up a mile up into the air, and our distance, the difference in our distance was inconsequential to the distance of how far away that ball now is, we would see the same face, right? So if we're going to agree that it moves, and if we're going to agree that a flat sphere would change its augmented perspective, we can both agree pretty happily, right? I hope we can agree that the moon is a sphere, right?
No. See, here's the thing. That was a very long, you know, I knew where you're going from the second you started talking, but you don't understand, and we don't have a solid model, but the flat earth says that there's a dome up there. Most of us believe that there's water above there, right? If you look biblical, and I'm not saying biblical is any proof, it is proof to some people, but you know, I like scientific proof that there is water in the sky, and the sky has some sort of transparent glass-like dome biblically. Right? So we see the sun in our azimuthal grid of vision. We see the moon in an apparent position inside of that. So here is a sample that I did. I cut my room in half. I'm hanging a light blue sheet here. 10 feet on the other side of the sheet, I have a light. This light is actually square, but it looks round. It looks like the sun or the moon, whatever you want. Okay? Now, my wife is over to the left of me, and I said, where do you see the moon? So she goes, oh, I see it right over. Let me move over. She sees the moon over here, right? So if I go over from her point of view and I put a little X on the sheet, she sees the moon right there. At the same time that she sees the moon over there, I see it right there. Okay. So we're looking at the same thing in two different positions at the same time from two different locations, all right? So now if we go back to the moon, right? We have, where is it?
By the way, pointless thing to mention, but you would know that was a square point source of light because you can see the kind of radiations of the diffusion of the light, right, in those four corners. No,
I disagree. Okay. Because on a round ball, it looks the same, and I'll show you that also. So let me, you know what? Since we're there, let me before we move, let me just go back to that element. Oh.
And the idea of the sheet is that we're assuming that there's a layer of water between us and
No, that's our grid of vision. The sky becomes our screen of how we see things in the sky. We've sent balloons up at nighttime with cameras looking up that could see all the stars, but when the balloon got to 60, 70, 80,000 feet, all the stars were gone. That's impossible on a heliocentric system, and you know it tells us how well we understand the sky. But if we look at well, you just asked me. What did you just ask me? You asked me.
Well, we're trying to agree that the moon is a sphere.
Yeah. No, you asked me about. Oh, I got it. So if this, I'm not going to tell you if this is the sun or the moon. What would you say?
It's again these visuals that you're bringing up. There's a lot to them. Camera aperture.
I'm making a point. Is that a sphere?
It's a point source of light.
Absolutely, it's a point. That's fine. It looks like a sphere. It could be a sphere. We don't know. But if we zoom forward, we see that it's actually a train with all different shaped lights on it. But
similar to the kind of laser pointer idea we had before.
Yeah. So what I'm saying is we don't know unless you can touch it, know how far it is, or anything. You really can't make any measurements.
But we do know how far it is.
We don't know. How do you know how far the moon is?
Well, okay, so this is something that
all right,
I'm certain we can agree on.
No. Don't be so certain of that.
I'm certain we can agree on this, Dave. We can be friends. I promise we can agree on this.
I have no problem, but I want to show you something. The optics of the sky. First, I showed you with the sheet that we're seeing things in different positions. So I'm in Connecticut, you're in Australia, and we're looking at the moon at the same time. I guess we could do that on certain time. And we're seeing a circle in the sky. Let's say it's a full moon. Okay, interesting, right? Here's a guy in water, and we're going to move the camera. Now look at his body. It's facing the freaking camera. That's him. His body's,
this is refraction of light.
Hold, absolutely. So as we move around, it's still going to face us and not distort. As we move around, his body's facing us. It's still facing us. So if that was the moon, that's how we see the moon, the same shape from all different positions.
And you believe that refraction is happening at that same level that you give in the example?
I don't know. I don't like looking up at the lights in the sky to prove the shape of the Earth. I can do that from down here.
Okay, cool. So, but here's where I think we can agree. I hope we can agree. So, back in my heyday, I studied astrophysics and physics at university, and I'm, as you can tell, a bit of a science nerd, and I'm fascinated by the subject, and I'm fascinated to collaborate in our journey together to try and test our hypothesis and try and find the truth. Because the whole idea of science is to try and see if we can find the truth. And when we talk about how do we know how far away the moon is, it's because you and I, and again, independent of one another, we can agree that if you threw a tennis ball on a wall and it bounced back and you could time the distance and the velocity of the tennis ball, you could kind of measure the distance of the wall. And as the wall moved further away, the tennis ball would take longer to come back. And we would both agree with how that element of physics operates. And what you can do, literally yourself, this is not something you have to trust or believe in some paper that was written. You can go to observatories, you can go to many universities, you can find someone that you trust or you believe in. You can use equipment. You can do this experiment yourself without needing to trust anybody.
You're going to talk about the reflector on the moon, right? That has been
Absolutely.
shut down for. You're going to talk about that, but what you don't understand is only people in NASA have access to that.
No.
Hold on. It has been shut down for years.
It hasn't.
And yes, it has.
Dave, I promise you can do it. I promise you can do it yourself.
Here's the thing. It's a trick. So it sends out like 500 billion quadrillion photons, a number that is unbelievable, and then it captures one.
It doesn't. That's not how it works.
Hold on. How is it hitting that reflector and coming back at the speed of light where we are thousands of miles or where we were supposed to be when we sent those out? It is a trick. And the other thing is they used they supposedly used the same technology before they went to the moon to figure out how far the moon was. Okay?
It's probably really important, important that we understand that you don't have to trust anybody. You don't have to trust NASA.
I don't trust liars that have been proven liars. I can prove that NASA lies about everything. I can show you 1,000 things.
Okay, so let's not worry about NASA. Let's not bring them in at all. Let's just talk about Dave. Yeah. And let's say that Dave, you yourself, you go to that observatory.
But this is a NASA trick. It's a NASA trick.
I'm not talking about NASA. It's got nothing to do with NASA. In fact,
so the reflector on the moon. Who put the reflector on the moon? Who put the reflector on the moon?
I believe it was Apollo 15. That when
NASA.
They put
NASA.
Okay, look. Okay, let's pause just for a sec. The question is not whether we believe NASA or not. So let's put that to one side. The question is there a reflector on the surface of the moon?
No.
Now, one way that we might infer whether there is or isn't is to look at our, let's say, technological arch nemesis, the other superpowers of China, Russia, who would be absolutely elated at the fact that they could so easily disprove. Do you not think they did the same experiment? Because if that wasn't there, they would be screaming from the rooftops. because they're independent space agencies and they'd love nothing more than to prove and show America's being liars.
You don't understand.
But the second part, so let's assume that that's not enough. I like my balloons there. So the second part for anyone who wasn't watching, I kicked off some animation on my thing. So the second part is, let's say, well, we don't just want to believe that because they could be in cahoots together. Maybe. What I'm saying is this technology is very widely spread across the world. Many universities have this ability. Many independent observatories have this ability. I'm hopefully, if there's one thing we can get from this conversation, is you can go and do this yourself and not need to trust anybody. You can watch that experiment being done, and it's not.
You can watch it being done by people with a computer. You don't think there's a computer program that says shoot 1 billion photons out and then wait a minute and then make a ping noise?
Yeah, but what if you were able to calibrate that laser yourself?
Like, you can't.
But you can, of course, you can calibrate lasers. Like when you're trying to do experiments scientifically, what you're trying to do is you're trying to disprove as much as you're trying to prove. Like if we could disprove that there wasn't a reflector on the moon, that would be an amazing feat of science.
How far away is the moon? How far? Just approximately. Do you know?
Oh my God! Now you're testing me.
It's all right if you don't. I can tell you.
I mean, I'm going to guess like 400,000 kilometers roughly. If my school was any good,
quarter of 1,000,000 miles. I think that's the same.
Yeah, okay.
It's 238,000 miles. But here's the question for you: is how come the moon only lights up the clouds that it's right near, and all of the other clouds in the sky are dark? How come? How can you have distant clouds, right? How can you have a distant moon only lighting up a small section, right? Get a flashlight, throw cotton balls all over your floor, hold that light up in the air, it lights all of them. How do you only light up a small section of them? Bring it right down low.
We can't compare the moon and a flashlight because the moon doesn't like.
Wait, the moon is light itself. Think about this.
It's reflecting light.
Well, so the moon is reflecting light. You believe that, right?
Well, I don't believe that. That's not a belief.
You've been told that. It actually is a belief. It's a belief. It's okay.
No, but here's something that's really important to understand. Again, when you're being educated in the sciences, we have different backgrounds. I'm trying to understand yours, and hopefully this is an opportunity for you to understand mine. We are not told to believe things at all. Quite the opposite. What we're taught to do is, how are we going to make an assertion one way or another whether something is true or not? Do you see what I mean? So it's not a belief of mine. This is a subject I studied passionately and something that I find very, very interesting. And I don't believe these things. I'm very happy to actually test them, do the tests myself if I have to, in order to find that truth. So the moon isn't an intrinsic source of light by itself. If you remove the sun, that you wouldn't see the moon as this big, shiny, bright object. It doesn't emit light itself. And by the way, hold on. By the way,
I'm choking to death.
Something just hit me.
Wait, I'd like to answer that.
Okay, so I'm so sorry. Let me just formulate this. In your model of this, let's say 2D sphere, ice wall on the outside, you have the sun and the moon.
I didn't say ice wall on the outside.
Okay, forgive me. Okay, but on the 2D plane, sun and the moon, opposite, and then the sun is emitting light and it's illuminating half of the Earth, right?
Not always.
So it's emitting up to half the Earth, and it changes and augments. In your model, the light from the sun would never be able to reach the moon because it's on the other side of the plane, right? So you would believe that the moon is not reflecting the light from the sun?
No, I actually believe that the moon is powered by the sun.
Fascinating.
The moon is its own light. The moon is its own light. So these are just, not that we trust NASA, this is a full moon because the sun is behind me. There's a full Earth, so there should be a full moon. But this is from NASA. How come the moon is
agree.
Hold on. Let me just. You talk a lot. I love hearing it, but I'd like to make a point now and then. So I'm standing right next to this cement ball, which is arguably more reflective than the dusty, dirty moon. But when I'm out on a full moon night in the middle of nowhere, I cast my shadow on the ground. I could read a book by it. How come there's not light bouncing off of this thing? I'm right next to it. Every time you double the distance to a light, it's a quarter of the brightness. Right? So if I'm looking up at a full moon and it's 1 lumen, halfway to the moon it's 4, halfway again 16, halfway again 64. When I'm 100 miles from the moon, it's brighter than the sun, multiple times. But that's not what we saw when NASA went there. But we don't want to trust NASA. Reflected light off of a dusty, dirty ball doesn't travel 250,000 miles to where you can read and it casts a shadow. I'm right next to this. It should be lighting me up if you believe that this is reflected light from the moon. It doesn't work that way. And also, there's a specular highlight. If it have a single source, how come the moon doesn't have a highlight? It's lit equally from edge to edge. And how come when there's a new moon, nobody could ever see it? Well, it's right next to the sun, Dave. It's too bright. Well, when there's a total eclipse of the sun, and not an angular eclipse, the one where there's no ring of fire, the earth shine, 6 times bigger and more reflective, should light up the moon, and you should be able to see it with your naked eyes. But no one's seen it with infrared, naked eyes. No one's ever seen the moon come, eclipse, or exit the face of the sun. No one has ever seen a new moon after it's gone new in less than, I think, 36 hours or 32 hours, something like that. 42 hours, something like that. But no one has ever seen it from anywhere. So what's going on in the sky? Not what they tell us. The whole thing about the moon is absolute insanity.
Can I try and understand that a little bit more? What did you say about the moon passing in front of the sun? What was that part?
So when there's an eclipse of the sun, there's supposedly it's the new moon doing that. How come nobody can, when the moon goes new, how come no one can ever see the moon? Well, they say because it's so close to the sun, it's so bright, you can't see it. Great. How about when the moon 100% eclipses the sun? Then the earth shine, just like the moonshine lights up the earth and I can read a book, it casts my shadow. How come the earth shine doesn't light up the moon so we can see it and take pictures of it? Oh my God, look at the moon in front of the sun. No one has ever seen the moon in front of the sun. No one's ever seen the moon come eclipse the sun or go away or block the sun or exit the face of the sun. No one's ever seen it. When you look into eclipses absolutely prove that it's not a globe. It actually proves it. Like when you see an eclipse like this, well, there's the moon right there. No, that's just missing sun. There's something blocking the light. You don't see a moon here. You imagine a moon here. You imagine a moon. You just see a missing part of the sun.
But don't forget, if you're looking at an eclipse here, does this not prove the contrary of what you said? You said the moon emits its own light. Now, what you're seeing here is as you look at the sun and the moon in front of it, the side of the moon that's facing you doesn't have an amount of light to reflect anywhere comparable to the amount of light that's hitting your eyes from the sun. So, of course, you wouldn't be able to see it.
Well, but no, you know what a total solar eclipse is? No ring of fire. When there's no ring of fire, okay? So
it depends on the aperture of your camera, but this is another trick.
Forget my camera. Every camera on Earth, no one has ever seen the moon during a eclipse. No one has ever seen it. No one's ever taken it from an airplane, telescope, observatory. Nobody has ever seen the moon eclipse the sun, right? No one has ever seen it at all. Now, do I think the moon is eclipsing the sun? Yep. But this is a deeper conversation because I think the moon is behind the sun. The actual moon is behind the actual sun, but we're only seeing the apparent sun and the apparent moon, right? But this is a conversation it's a whole nother podcast, but I can't get deep into these things because you're having difficult time understanding the simple concepts that I'm going over here. So this is proof that it's not the moon in front of the sun. You would see it. Now, I don't have a picture of a total solar eclipse here. I'm just showing you, like, you should be able to see it even with this ring of fire, right? But no one's ever seen it. That you got to say that's weird.
That no one, when you say no one has ever seen it, are you expecting, like, what is it that you would like to see?
The moon.
That would make you feel happy? You would like to see the moon in its full illumination?
No, just the moon in a dim, faded moon. Reflect, the earth shine. Look, I can read a book by moonlight. The earth is 6 times bigger and highly reflective compared to the moon. So the earth shine on the moon, because from the moon's point of view, there's a full earth. The earth shine should light up the moon like a Christmas tree, but it doesn't.
I think the reason why I disagree with that is because it's very hard for us, I'm putting myself in the same bucket. It's very hard for us to have perspective on such vast distances, right? Because actually the Earth is like this tiny little speck, just so far away, and you might look at it and say, oh, it's really reflective, but actually if you think about the angular size of the moon, how far away it is from the reflective Earth, I can see it's like, no, in a new moon, the Earth is not reflecting light from the sun enough to illuminate the face that's hitting us in a new moon. I disagree with...
So the Earthshine isn't bright enough to light up the moon, but the moonshine is bright enough to light up the Earth.
But
what you're saying?
Remember, the moon is reflecting light from the sun. It's not.
And the Earth doesn't reflect light from the sun.
It does.
Okay, does it reflect it more, less, or the same?
I think. Let's say, for argument's sake, if I'm trying to take your side and I'm trying to steel man your argument, I would say it probably reflects more light into space.
Let's even go with the same.
Well, then, if you were standing on the moon, you would see a bright Earth.
Well, and you'd be able to read a book by it, right?
Well, I guess, and I guess this is about the perspective of which body you're standing.
Why wouldn't you? We have 6 times the brightness coming off of the Earth to the moon. You should be able to read a book, right?
Well, then let's imagine that me and you are astronauts, and we jump on a rocket and we go and land on the moon. And then what's happening? And I'll try and do this for the people listening too. We say we've got the sun, and then the Earth, kind of linearly in front of you, and then we are on the moon, where we have the Earth in between us and the sun. So just imagine that for a second. Are you proposing that if we are in daylight on the moon,
you wouldn't be in daylight. You'd be in darkness because the sun's on the other side of the moon.
No. Forgive me if I didn't explain that brilliantly. So me and you are standing on the moon, bright daylight because the sun is directly above us, right? So we are having a moon day. And between us and the sun, the Earth is somewhere there too. Are you saying that the amount of light that the moon reflects should be bouncing off of the Earth so we could see the Earth in an illuminated Earth? Is that what you're saying?
So are you saying that the Earth is eclipsing the sun from the moon?
No, it's not eclipsing it. It's almost like a new Earth. So we can see the sun, the Earth is right next to it, and my argument would be we wouldn't really be able to see the Earth.
Right,
because we've got this massive bright light screaming at us.
What if the Earth went completely in front of the sun and blocked the sun, but the sunlight was still lighting up the moon?
I think that would be fascinating to see, because obviously the angular size of the Earth would be so much smaller in comparison. So I don't know. I think I'm trying to get my head around that.
We're getting into Narnia space magic when we don't need to go there. Let's go. I still want to go back to seasons because that's important, but let's talk about one physical measurement of the Earth. Okay. The Earth is how long? How big is the radius of the Earth? How big is the circumference of the Earth?
40,000-ish.
24,901 miles around. We're talking kilometers, miles.
Roughly. I honestly don't know.
You got it.
Someone's going to Google this and go, he doesn't know stuff. I just genuinely don't know.
No, that's okay. That's all right. All right. Because we study both models here. Mm-hmm. So we got a guy on water at rest when contained lies flat. And when it gets cold, it freezes flat. So we got a camera 6 inches off the ice here. And he laid out these 4 lights here at 8 miles, 7 miles, 6 miles, and 5 miles. Now, that doesn't seem like far, but if you use the Earth curve calculator with a 6-inch viewer height, these lights should be, and I'm rounding way down, and I'm adding their stupid refraction in there, 30 feet below the curve, 22, 15, and 9 feet below the curve. But for some reason, they've refracted up and stopped at eye level, all on the same plane.
One of the things I would try and challenge you on, and I don't challenge this in a disrespectful way. I challenge it because I have done many experiments in my time where there's been some fundamental either overlook or error in my calculation where the maths that I thought was correct wasn't correct. Because
go do the math yourself. go 8 miles, 6-inch observer height. Go to earthcurvecalculator.com and put in the calculations, and then divide it in half if you want. You give the Earth, just say, it's half wrong. It doesn't matter. It's wrong. It's absolutely 100% wrong, right? And we have so many observations that absolutely blow away the math. And the thing is, the Earth, they have to just make up magical refraction. Now, here's the question: if something's refracting up, Why does it stop at eye level? Why doesn't it go thousands of feet in the air and refract up in the air? Here's a spot. Now, yes, we're on a mountain. I think it's a couple thousand feet high. And it's hard to see here, but we have all these mountains that are over 700 miles away. There is more. It's closer to 60, but I rounded down to give the Earth every benefit of the doubt. 50 miles of missing curvature. The tops of these mountains should be over 50 miles below the curve, physical curve, if the Earth is a globe the size that they say. So you have a couple options here. One, the Earth is bigger, but if the Earth is bigger, everything about space is wrong. So it can't be bigger, right? And the only thing that they can say is that these mountains are refracting up and stopping at eye level. Okay, the mountains are here. You can go do this yourself. You can look at this picture. You can look it up. And then over here, there's more mountains, and these are even farther away. Didn't even calculate how far those would be gone. But we can see them. They stop at eye level. If refraction was a thing, why don't they refract up in the air? How come when I go higher in the air, they stay exactly where they are? They don't rise up with me. How come?
Or alternatively, why does the horizon not continue further if it's flat?
Well, because you can't see, right? You can't see forever, and the horizon, due to perspective, not only goes from left to right, the sides come in, but it also crunches from back to front. Okay, let me explain what that means. Okay,
but your diagram that you showed brilliantly earlier, that with the grid lines that we explored through the tunnel, if this was flat, you would see that extend off into infinity, and it would still slope up more into almost like a point.
That's not correct. That's not correct. So we have these arrows here. Okay, from this arrow to this arrow is whatever distance. Between these two lines here is less of a distance, right? That's what it looks like with this.
That's what it looks like.
Yeah, but you don't have much perspective here. So let's look at this. So it's hard to see here. This is the shoreline where I'm standing. This is pointing to this island, which is about a quarter of a mile out here. And then this one's pointing at New York City, which is 25 miles away. So from here to here is a quarter mile. And from here to here is 100 times that distance compressed into this little area where you don't get much information. You don't get much information. So if we add a little boat here, this boat gets smaller here. It gets smaller there. And then it's got to get the same amount smaller 100 more times before it gets to New York.
And the reason why we can't see past New York is because of the atmospheric lensing issue.
You could actually. This is a pretty clear day, and if I zoomed in, I could actually see New York. I could see the buildings. I could see everything. And
if you zoomed in further, you could see London.
No, absolutely not. You can't see that far. The thing is, I can see underneath the Whitestone Bridge. The Whitestone Bridge, from this distance, should be 460 feet below the curve. But not only the stanchions on the bridge, I can see them. I can see the deck of the bridge. I can see under the bridge, and I can see the footings below the decking.
But then there will be something wrong with the mathematics.
Well, that's what you say because you are in a globe religion, and you say, if I can see beyond with the limits of a physical ball, something's wrong with the mathematics because you have a globe religion.
Well, I guess it's not a religion, I promise you. It's not like a belief that I hold because I was
So I showed you evidence that we can see too far. Show me evidence that the math is wrong.
That's a really good challenge, and I appreciate that because that's something that I would probably like to do.
I could help you, though. The 8 inches per mile squared is wrong after 2,000 miles. After 2,000 miles...
What do you mean? What does that mean, 8 inches per mile squared?
So 8 inches per mile squared, the Earth curves at 7.998 inches per mile squared. So
out of interest, sorry, why squared? If we're talking about a linear distance, why do you square it?
Because it's not linear. So you're here, and you go out a mile, the drop is that much. If you go out 2 miles, it's not double. It exponentially goes down, and it becomes a parabolic equation. So after 2,000 miles, it doesn't work. It actually predicts less curvature than there is. But you can't see 2,000 miles. You can't see 1,000 miles, right? Because the air on the clearest of clear days, it becomes opaque in that distance. So from New York, you can't see the UK because it's too small and the air is too thick.
I got to be careful what I say because I'm trying to think on the fly and I don't want to embarrass myself. But my natural instinct when you talk about there being a parabolic relationship with the drop-off, it wouldn't be. A parabola is more like a
Well,
like
the thing is, when you look
like
to try to
like
verify,
a cone almost, right?
when you try to verify the curve calculator, they're going to claim parabola. But yeah, we agree, it's a parabola after 2,000 miles.
But the curvature of the Earth isn't a parabola, is it?
The curvature of the Earth is spherical. There's four formulas. The 8 inches per mile squared actually gives the globe the most amount of leeway. It is. So we use the one that gives globe the benefit of the doubt. But we don't have to go that far. 10 miles, there should be 66 feet of curvature. Did you know that?
No, but I'm still bothered by the square. I'm trying to understand why there is a quadratic relationship with that experiment.
Yeah, I'll show you. It's literally the Pythagorean theorem. Okay.
Forgive me for being that guy because I don't mean this to come across wrong, but just for context, I have a degree in physics, right? So I have gone through quite a lot of issues or problems in experimentation that rely on these equations being correct. And the only thing I'm bothered by slightly is if me and you are both collaborating again, we're trying to figure out the drop in distance below the horizon with a linear increase in the distance of the object. Yeah. I am not sure that would be a quadratic relationship. I don't think it should be a square.
Let's take a look. Do you believe in the Pythagorean theorem?
I don't believe in the Pythagorean theorem. I don't believe in it. It's not a belief. It's just a factual kind of mathematical
thing. So you understand that the Pythagorean theorem is describing a real relationship between distance and length and angles, right?
Yes, it's describing the relationship between how an angle will change the size of a triangle. Yes.
Okay, great. A squared plus B squared equals C squared. Do you believe that's a correct formula?
Again, I don't believe it, but yes, this is a correct formula because we can prove it and we can also derive it.
So great. So we have a guy standing on the top of the Earth, right? Mm-hmm. And we draw a line out from the bottom of his feet straight out. We don't follow the Earth curve. We take the radius of the Earth, which is a point from the center to the guy's feet, right? And then we say the drop would be this little area right here. This would be the drop. So whatever this distance is, this would be the drop. Okay, am I doing it correctly?
I'm with you so far.
So they say the radius is 3,963 miles. And let's say we go out 100 miles. Of course, this isn't to scale, but a sphere is a sphere and a distance is a distance, right? So we say we take the miles squared and we add them up and we say the hypotenuse is 15,000. We divide it out and it's 3,964 feet, right? And we divide.
So, out of interest, you've got 100 miles. Why the change in units there? You got 100 miles across. How's the hypotenuse 3,964?
Well, so we took the square of the radius and the square of this, right?
And you've assumed that's 100 miles, yeah. So why are we not keeping it all in miles for the sake of just clarity?
It is all in miles. Well, okay, it divides out to 1.2615 miles. Right? 1.2615 miles would be the drop. So, and that turns out at 100 miles, 6,660 feet. Okay? And that is at 100 miles, 8 inches per mile squared. So take 100, square it, times 8 inches, divided by 12 equals 6,660 feet. So 8 inches per mile squared is the Pythagorean theorem. Do the calculation. 100 times 100.
Checked, yeah,
100 times 100 times 8 inches. So 8 inches per mile squared. Square the miles times 8 inches. Divide by 12 to give you the number of feet, and it's 6,660 feet or 1.2615 miles. Okay, that is correct. And so we know that the 8 inches per mile squared is actually giving the globe a tiny bit of favor. I think it's off by less than a foot, but in favor of the globe. In favor. So again, we don't need...
But also, firstly, thank you for this. Because I can see that there's a lot of work and thought that's gone into this, and that there's quite a lot of information and a lot of numbers for us to follow brand new to this. So while it's going to be interesting for me to try and break this down later and try and understand it better, when you look at New York, you don't look at that like 100 miles at an angle upwards in space, do you? That's on the horizon. And in your diagram here, this 100 miles just kind of extends out into space.
Well, if you want to go 100 miles forward on a flat Earth, you're going to be on the flat Earth 100 miles from where you are. But if you want to go 100 miles forward linearly on a globe Earth, you're going to be 1.2615 miles in the air unless you account for curvature. If I built a road straight out from underneath my feet and didn't account for curvature, it would be over a mile in the air if I didn't account for curvature. No one ever accounts for curvature. No roads, bridges, tunnels never account for curvature. All
because
construction is
because level is the closest to the
level's
earth,
curved. Yes, your level is curved. I understand that's a globe mental gymnastics, but I don't play that game.
Globe mental gymnastics.
Globe mental gymnastics. Curved, yeah. Level's level. Plumb is plumb. All plumb bobs are parallel, right? All ground is horizontal. There on a globe Earth, there are no parallel lines. You can't have a parallel line on a globe Earth. There's no parallel lines.
I would actually kind of agree with you in some respects with that.
Yeah, but there are parallel lines. There are parallel. Look at the World Trade Towers when they were here. They were plumb. They would be wider at the top if the Earth was a globe. They were tall enough to have several inches of distance at the top. Right? It's crazy when you look into this. Here's the thing. Listen.
So that's not something. Okay, go on. I'm listening.
Mark, all of this stuff is being censored. You're not allowed to. They don't want you seeing it. On my website, flatearthdave.com, I have an app. An app's $3. You can get the app or not. It doesn't matter. Scroll down to where it says crash course. You see a big picture of me, and then click that. There's a list of videos there that Google's hiding from you. And part of my challenge is, if you want the 3 Bitcoins, anybody that's listening, you have to watch at least 3 of those videos. I think there's 15, 20 videos, 30 videos, whatever. Watch the first 3, and then you're screwed, because you're never going to be able to see the Earth as a globe again. Right? The other way to do it is on my app. Every day there's a featured video. Watch the featured video every day for 2 weeks. At the end of that 2 weeks, if you think the Earth is a globe, you hit the question mark button, which is the frequently asked questions, and up comes all of the questions that you might ask, and they're all answered there. You know, like, where does the sun go? Why would they lie? That's my favorite. Why would they lie? Mind-blowing stuff in there. Mind-blowing.
Do you know what panics me a little bit?
What panics you?
Is
that the Earth might be flat, and that your entire life world belief is crumbling to an end because of this podcast?
No. What's panicked me is, when I was thinking about coming on to do this, a lot of people had brought your name up. People in my circle said, "Oh, you've got to go and speak to Dave," because what's panicked me is I came into this conversation because I'm really interested to try and find the common grounds, right? The commonalities. Sure. How can we work together? Maybe there's things about my understanding that I'm not sure about, maybe vice versa. And maybe between us, we can decide on things that we can test together without needing to trust any authorities, that we can figure this out. And what's panicked me a little bit, probably wrongly, I hope wrongly, is that in this involvement of like an app and asking people for this idea of 3 Bitcoins to go and start watching videos and buy the app for $3, it's like, I hope in my heart that you're not somebody who is unwilling to contend with the consistency of the angular momentum of the sun or the spherical moon, or I hope that you're not wanting to contend with ideas because you're trying to monetize it.
I say don't buy my app. Just go to the crash course. That's all you need, right? But a lot of people, because they want to learn more about flat Earth, they do get the app and they love the app. Go just read the reviews on the app, but don't get the app. Whatever you do, don't get it.
It worries me a little bit, because
you can worry all you want. Don't get the app. Nobody get the app, okay? Do not download my app. Just watch the videos on my website. They're all free. You can't miss it. Go check out my YouTube. Go check out my social media on my website. My YouTube channels are amazing. My interviews are amazing. And there's tons and tons and tons of stuff. Watch it. Instead of just saying, oh, the Earth is a globe, I'm not going to look. That's ignorance. Ignorance is not good. I'm ignorant to everything I don't know.
I agree with everything you I don't know. I agree that ignorance is a very, very dangerous thing, and between the two of us, we're hopefully going to get the world in a better place in terms of trying to find the truth. Now, as we wrap this up, I appreciate your time.
We have to double back the seasons. You asked how seasons work.
You know what? Let's do seasons, and then hopefully we can, because I appreciate your time as well, and we can do this again down the line when I've had some time to get my old maths books out.
I hope you put this whole thing out unedited. I think you're a good guy. I think you're asking good questions. All right, this is awesome. So you and I are outside. You're a girl, by the way. Okay,
I'm fine with
that. Of course. Okay. So we got somebody out here, and they're holding a heat lamp. It's freezing cold outside. They're holding a heat lamp above you, whatever, 15 feet in the air, whatever it is. Okay, and you're warm. Okay, and you say, "Hey, I see the sun right up there, and I'm warm. I'm cold because I see the sun farther away and it's low in the sky. Now, this person slowly walks over to me without changing the height of the sun. Now I see the sun high in the sky. I'm warm. You see it low in the sky. You're cold. That's how seasons work. That's how seasons work.
I understand the diagram.
Yeah.
And I think that if you were to distill the system down to what you've put in the diagram, I can agree with you.
Yeah.
You know, distance to the heat source, warm or cold. But the problem that we still aren't necessarily facing is if the sun is moving between these different tropics, either which it is according to your model, when it's in the tropic with a much larger radius, it has to kind of move quicker, and in the one with smaller radius,
evidence
it has to
of that.
Move slower.
There is evidence of that.
Maybe, but then the evidence would be the best way of looking at that is you could boil this down to two problems. Either the seasons are different lengths, or the second option is the angular velocity of the celestial bodies is changing. There's actually only two answers. Now, we know between me and you, we don't have to ask anyone, we know that the seasons don't change lengths. We know that summer is the same as winter. And we also know that the angular velocity of the sun doesn't change based on our pictures. Or at least we can maybe debate that still. Yeah, so my worry is this is actually one of the pinnacle criticisms I'd like to double down on, because I believe we are both solving this problem. We know that these two things can't be possible, therefore we know that we can't have
let's just talk about that for a second, because if the ball is tilted and going around the sun, the north should have the same season 6 months later that the south has, but the sun arcs around the north. So if you're inside of the Tropic of Capricorn, the sun is arcing around you. So that's the Arctic region. That's the Arctic region. But if you're out here in the outer area, the sun doesn't go around you. It comes towards you and then it goes away. It's antarcing. So that's the Antarctic region, right? The Antarctic, okay? It's antarcing and it's ticking. It's a clock. So why is it that Antarctica is the coldest place on Earth, but supposedly the sun doesn't set for 4 months in the winter? How is that possible, right? How is it possible that at 60 degrees south, that's even before Antarctica, there's no plants, there's no animals, there's nothing. It's just cold, and there's no life beyond there. But at 85 degrees north, 85, which is significantly more north. Remember, we're on a ball. There has to be symmetry that there's plants, animals, and people thriving, okay? At a much farther north. It should be the same, but it's not. And that's because the sun isn't always near here. But when the sun is in the inner north, let me just move it to the inner north.
And forgive me, but there isn't actually a mechanism moving this, right? So in your model,
when you say mechanism, is it God? I don't know. This is an intelligently designed world. This is an intelligent design world. I didn't used to believe in intelligent design. I believed in the Big Bang and evolution. But then when I discovered that this place is intelligently designed, I had no choice but to understand that there's creator. In the north, the sun is staying very close all the way around. Look, I'm right here, and it's never very far from my finger, right? That's how we can have 24-hour sun in the north, right? But out here, the sun goes really far away, comes close, far away. It's antarcing, the Antarctic, the Arctic. It's arcing around me, right? Seasons make zero sense on a globe Earth. They make perfect sense on a flat Earth.
Okay. That is because I won't rewind back to the original conflict that I believe we have, because I can appreciate your model. If you were to hypothesize, how do you think those bodies are suspended and moving? If you were to try and,
I don't think that they're physical objects at all.
You think?
And again, you've spent 99% of your time looking up at the lights in the sky. In your world, right? So if I had a box of air and I went into a room that was a vacuum, so there's no air in that room, and I put a hole in that box, what's going to happen? The air is going to violently...
Because of the difference in pressure.
The air is going to violently fill the available space.
Correct.
Okay? So, and we're told that gravity is holding the air down to the earth. That's why the negative torque 17 vacuum of space doesn't pull the air away, but I can, with my weak low pressure of my mouth and lungs, pull air and water up and away from gravity close to Earth where gravity is the strongest, but the torque 17 vacuum of space can't pull it away. And then
don't forget that there's a gradient of atmospheric density. So it's not like the vacuum is constantly like pulling at Earth, right?
So that again, this is called globular mental gymnastics, because in a tank, if I had a half a tank of propane, it's liquid on the bottom, it's a thicker gas in the middle, and it's a thinner gas on the top. But if I put a hole in that tank anywhere, all the gas is gone.
It's important to distinguish.
Pressure needs containment. You can't have pressure without gas. Now, you could say, correct, you can't, except if you have gravity. Gravity holds gas down. There is zero evidence of that.
There's zero evidence that gravity holds gas down?
Yes. There's zero evidence, because I can pull gas away from the Earth with my mouth and lungs.
If my mouth and lungs was overriding gravity, yes.
So is the low pressure of my mouth and lungs stronger than the no pressure of space? Give an honest answer. An honest answer. The vacuum of space is stronger than my lungs.
The mistake I think that we both might be making is comparing apples and oranges, because what you're actually saying is, can I make enough of a pressure difference to move this volume of gas up? So relative to this room that we're in, if you were to, suck some air up or whatever, then yes, you've got varying different pressures between what you can do in your mouth and
let me go this way. I've got a gallon jar, and I go into space and I seal the jar so that there's nothing in there, and I bring it down to Earth. Let's say it doesn't explode or implode. Okay, and if I turn it upside down and poked a hole in it, it's going to violently suck it in, right?
Yeah, because there's a big pressure differential. Yeah.
Okay, but with the very tiny difference in pressure in my mouth and lungs, I can pull air and water up and away from Earth. How come it can't do it farther away from Earth where gravity is less?
Maybe because I think you're envisaging the vacuum like something that is
sucking. No, I don't envision that.
Your mouth is sucking.
This is what globers envision, flat earthers envision. We know it doesn't suck. We know that it's just no pressure, low pressure. It's a difference in pressure. Pressure means a container. You can't have gas pressure without a container. Hey, come over, have a barbecue. Okay, bring over some propane for the barbecue tonight, but don't bring tanks. I don't like tanks. Bring it just over without a container. Can you do that for me?
Yeah, but what your actual point is to say, unless the Earth was contained by something, it couldn't have atmospheric pressure.
Correct. That's what I'm saying.
This is what I mean. This is cool, right? Because this is where we get to exchange the positions and ideas between the two of us, because now I think I understand more what you mean. But I guess I would propose that if your belief is that you can't have atmospheric pressure unless it's in a container, you would in a way have to say that gravity kind of doesn't work, or at least doesn't exist in the way we think it is, because what you're saying is the Earth as this massive object which is drawing things towards it, that force is not enough to attract gas to form atmospheric pressure. It seems like that's what you're saying.
Well, it's when you start looking into it, you realize that it just doesn't make any sense. We send balloons up and they land east of where they landed. They should have landed 3,000 miles to the west because the Earth is spinning underneath them. They say that the atmosphere is spinning with the Earth. That means that the higher up you go, the atmosphere has to speed up just to keep up with the ground under it because it's making a bigger circle, just like the outer loop of the sun, right? But for some reason, we send balloons up. They're up there for 3.5 hours and they land east of where they started. They should have landed 3,500 miles to the west, but they don't.
But if we just focus for a second on this idea of the container that you bring up, because I feel like I've understood your point there, or at least I've understood your perspective. Am I right to infer that you think that gravity isn't there, or how do you believe things are?
Gravity is when we're talking about Einsteinian gravity or Newtonian gravity, because Newtonian gravity they've changed with Einsteinian the bending and warping of space-time, which is just a fantasy. But the gravity is a made-up theory, disproven. And everything is electrostatics. That's what makes things go down. The Earth has a negative charge. The sky has a positive charge. And anything in between, anything above the Earth, it has that positive charge and is attracted to the non-moving Earth below.
You believe that the reason why I'm sat in my chair is because I'm electromagnetically attracted to the Earth?
Everything, without exception, from air, from you to everything, is electrostatic.
Well,
everything.
I would be able to measure the electromagnetic force.
You can. So let me show you how you can manipulate it and charge it. So here
but this means that I'm going to be able to fly, right? Because I can get a polar opposite.
Well, if you get struck, if lightning strikes next to you and changes the polarity of the Earth for a split second, like it does sometimes, you go flying in the air. It happens many times. It happened during some events in New York City, which that's a whole nother story. But here we have some balloons left over, and we have a button here, and it's just neutrally buoyant a couple inches across the floor. But this wire is connected to a Van der Graaf generator, and we're going to add a positive charge to this. We're going to increase its positive charge, and when we do, it goes down. Now, did we manipulate gravity, or did we manipulate the attraction, the electromagnetic traction? We discharge it, and it goes back up. And then we could do the opposite, and you've seen this before. We can put a negative charge into this. It goes up. Turn it off, it goes down. If we put the negative charge in and keep it on, it goes up, it stays up. Are we manipulating electrostatics, or are we manipulating gravity, right? We're manipulating electrostatics. Here's a drone. This is a drone from MIT, right? It's called the silent drone. It's got no moving parts. It's just changing its electrostatic potential, and it can fly. Okay? This is electrostatics. This is why things go down. This is why during electrical storms, things fall at different rates. Right?
I would be able to take a measurement of the.
This has all been measured, right?
But I know, but here's what I mean. If we went, we could see the measurements of the electromagnetic forces that are applying to that object, and then you could come to me when I'm sitting in my chair, and you'd see those forces on there. Right. That same electromagnetic field isn't there. That's because they're different forces entirely.
Here's the thing. I'm with you. Let's pretend gravity's real. Now, your gravitationalist, heliocentric masters. Religious leaders, no offense, let's make them fun. They say that the electrostatic force is 10 to the 36 power stronger than gravity. 10 to the 36? Do you understand what that number is? Because I don't. Right?
Well, I'm aware that gravity, if you're lining up the forces, can be considered as extremely weak in comparison.
Okay, but 10 to the 36 means gravity has zero force. Like if I came to England right now, it doesn't mean it has
zero force. It just means it's relatively weaker.
Relatively weaker. So let's say I come there and I punch you in the shoulder and you're like, ouch, Dave, stop it. Right? Then I punch you 100 times harder. I'd probably send you to the floor. Right? And then you're like, what'd you do that for? Then I punch you 1,000 times harder, probably break your back. 100,000 times you're dead. 1,000,000 times what the hell happened? Right? 100 million times, 1 billion times, 1 trillion times, you would probably explode. 1 trillion is 12 zeros. We got to get to 36. We got to keep multiplying that number times 1,000. Like how many more times? It doesn't make any sense. It's basically saying that the gravitational force is zero in comparison. I just proved that electrostatic forces are real and work and are manipulatable, right? Gravity has no overriding bearing factor on it. That's like getting the biggest crane, bulldozer, biggest earth-moving dirt machine in the world and compare and say, okay, I've got a gnat. That gnat is closer to it, the strength of that than the difference between electrostatics and a gnat is a mosquito, a very small mosquito. All right?
Well, I have an idea. If we agree,
again, you gotta understand. This is what they say. I don't believe them. 10 to the 36, forget it. No one can even measure that, right? But they're admitting gravity has no relevant force compared to testable, measurable, repeatable, observable things that I just showed you that you want to ignore.
I don't want to ignore them. I promise you.
Okay.
If you take a substance where electromagnetic forces can't permeate, where electricity can't flow, whatever, I don't know, take some melted rubber and you drop a heavier rubber ball in it, the ball would still go down despite not being affected by electromagnetism. You
ever see the Hutchinson effect where he's making things fly all over the place and do all stuff with electrostatic forces?
Well, I don't want to argue with you that electrostatic forces are absolutely real and they're there. Electromagnetism is very well understood. We use it all the time. You lift a car with an electromagnet. It's really important to distinguish the very fundamental difference between those structures. They're very, very different ideas. We can measure both. We understand both extremely well. So the not worrying thing for me, but the thing that I find difficult is to understand how you get to the conclusion where you go, gravity is basically a lie that's been perpetuated to you.
Show me a proof. Show me a proof. Show me a test. Show me anything that proves gravity. And when you say the guy with the 2 lead balls in his barn, you really haven't looked into it. 2 lead balls, right? How come a plumb bob next to Mount Everest doesn't go a little bit sideways? It's absolutely ridiculous. And if you
But
look at the
again,
gravity,
it's because of the lack of perspective.
you know about the
me and you both
three-body
have with the
problem?
Earth.
You know
The
about
Earth
the
is
three-body
huge,
problem?
right?
You know about the three-body problem?
Is this the problem that you can't predict the outcome of three gravitationally
Correct.
attracting
And
bodies?
that's just three. We have hundreds in our solar system alone, let alone our sky, right? In our galaxy, 100 billion stars, all of them have have orbiting moons and planets and all this stuff. That they say 80% of the stars in our solar system are binary or trinary, which means they're going around each other, right? All of this stuff is going on. The Earth is traveling at 4.5 to 5 billion, no, 4.5, 5 billion miles a year, never to return to where it was before, right? Never to return to where it was before, right? We're moving at all of these distances. Hold on. Here we go. Turn that off. All right. So we're moving, chasing the sun, right? All the other stars are doing all of their motions. We're going 193 million miles from one side to the other, chasing 4.4 billion miles a year, never to return to where we were before. And never once have two stars changed position due to parallax. Never once have we ever saw two stars cross each other's path. Yes, they make circles around Polaris, but never once have they ever changed position. Never once. Right? How come in June at midnight, when I look out at the stars, I can go out in December at midnight and see the same stars? I'm looking in the opposite directions on the other side of the sun, but I can see the same stars. Wrap your mind around that one.
That's not correct.
It is correct.
It depends,
you can't see all of the same.
Where you're standing on Earth, but it's not
can't
correct.
see, but you should be able to see none of the same stars, right? Now, because
not
of the
quite, depends where you're
precession of the
standing,
stars, the stars circle around, and 6 months later, we do have different zodiac stars next to the sun. But the other stars, you can still see them. You can see Orion all year long, everywhere.
Well,
and that makes no sense.
This is really something that's great for me to have a little look into, because I really want to thank you for your time. I appreciate the conversation. Believe me, obviously we don't share the same ideologies, but I think between us, maybe we do this again down the line and we unpick some more of these things. Now, the last question that I did want to wrap up with to ask you is, in your opinion, is there anything that you would like to see, or any kind of test that you believe in your heart would be a definitive proof? What is that test?
So, thanks for asking. Let me just get it. Where is it? So this is a test that would put this to bed forever. All right, and let me just get here. I'm gonna clean this up. So
take your time with the screen share, and I guess for all of us listening here, what we're looking for is just. Is there a way that we can come to a consensus? Is there a way for Dave that he could see some kind of objective test or experiment which would console this situation?
So here it is. Okay. So Antarctica, they tell us, is a continent at the bottom of a ball. They say it's about 10,000 miles in circumference. Okay. So here is Santiago. We get two airplanes in Santiago. We fly them to Antarctica. We land. We prove we're in Antarctica. We get teams of people, flat earthers, globe earthers, scientists, everybody on each plane. The planes take off. They fly at a low altitude so you can watch the shoreline, so they can kind of see, all right, we're flying at a normal speed, and go in the cockpit and see they got the engines at 80% power or whatever. And you'll be able to see, and they follow the shoreline. Now, if the Earth is a globe, it should take 10 hours and both planes would meet over in on the other side. So if both planes landed there in 10 hours, that's interesting, right? If the Earth is a globe, both planes would have to go all the way around, and it would take about 68 hours.
Sorry, do you mean if the Earth was flat?
I'm sorry. Yes, thank you. Thank you so much. If the Earth was flat, it's about 68,000 miles. So at 500 miles an hour, it'd take about 68 hours to go. So that's a huge margin of error, because they'd be following the shoreline all the way around, right? So this would prove that the Earth is flat. However, there's a problem. One, I don't know if the plane can't fly that far, so they'd have to bail and get fuel, and that's a problem. But it doesn't prove that the Earth is a globe, because maybe the Earth is set up like this. there's a base right here, and they're saying this is Antarctica. They're saying there's another base here on this continent. They're saying that's Antarctica. And off of South Africa, there's another base here. That's Antarctica. Do you know that nobody has ever gone from this base to this base? Which I
didn't know that, firstly, but one thing that's probably important is the question I'm trying to understand is what test for you would give you a definitive proof?
This is the test. I'm going to finish finish it. So you got your different bases here. They're just not on the same continent. So after the planes, if the planes say, hey, 10 hours, we're here, then they just have to, within 4, 5, 6 hours, even give them 7 hours, 8 hours, they'd have to fly to Australia. And if they flew to Australia, that would prove that the Earth is a globe, but it'll never happen because the Earth is flat.
Well, I mean, I'm just thinking 3 Bitcoins, roughly $60,000 ish, probably more, 60, 120, 100. You got like near 200 grand with the 3 Bitcoins. Why don't you just like get a couple of private jets and see if you can? Because
they won't let you. Antarctica is off limits to independent exploration beyond 60 degrees south. Yes, you can spend $40,000, $50,000, go to freeze your butt off in a little camp where you're going to see some stuff. You know, we actually have guys going this December. There's a thing called The Final Experiment, which is literally just a false premise, but we don't care. Where our guys are going, we're going to observe the sky. And if we see a circling sun, which I don't believe we will see, if we see a circling sun, that just tells us how much we understand the sky. You spend 99% of your time talking about the sky. I can show you measurement after measurement after measurement, physical measurements of Earth that prove that the Earth is not bending, right? If something doesn't curve, then it's what? Because every test for curvature has proven none. And if something doesn't move, then it's what? Every test for axial rotation has proven the opposite. You know about the Georgia Guidestones?
I'm not, but I have to ask if we can maybe keep that for the next episode, because I would love to do this with you again, and I would really like to take first dibs on those Bitcoins the moment that we finally get there.
But here's the thing. Yeah, because I don't listen. You have if you really think you got it, you gotta find somebody that has the app, so you don't have to spend the $3, and go to the frequently asked questions.
I'll support you, Dave. I'll get it.
It's okay. The frequently asked questions page, because your proof has already been answered. What you think is already, it's 99% chance it's already been answered in there. So again, the test is not to disprove flat Earth, right? Because I could disprove. You can just make up anything. You have to prove the globe. Prove the globe. That's it. Very, very easy.
Well, I've got to say, on that note, I'll look forward to a day that we can come to a consensus on that. I do feel like we both understood each other a little bit more. We've got some more stuff to figure out. I've got some maths to look at, but what a pleasure, Dave. I look forward to doing this again at some point down the road.
All right, Mark, that was great. Thanks so much.
Nice one.